So let me introduce our next speaker. Just give me a minute. So I think you can see my screen.
Yes.
So our next tutorial is from Rockport Networks, and it will be presented by Matthew Williams. He's a CTO, and he has 20 years of technical leadership and engineering experience, 11 years as CTO of a successful network technology company, and has several US patents. He's an expert strategist, analyst, and visionary who has delivered on strong product visions and obtained buy-in at the highest levels of Fortune 50 companies. He's an insightful and energetic communicator who enjoys product evangelization and inspiring global business and technical audiences. He has a degree in electrical engineering from Queen's University. So let's welcome Matthew Williams, and he will be talking about addressing network congestion with a switchless, ultra-low latency HPC Ethernet solution from Rockport with market-leading performance under load. Matthew, welcome, and please share your slides. Yeah, get started.
Okay, well, thanks for the introduction. Make my screen sharing going.
Yeah, we can see it.
All right. Well, welcome everyone, and thank you, DK and Hari, for being the opportunity here. What I'm going to be going through to start with is talking about network congestion itself, why it's important, and what aspects of HPC it actually impacts. We'll go through a detailed view on what Rockport's architecture looks like, and I'll share some benchmark results from our current firmware release. Of course, take any questions if time permits. So first, network congestion. So broad set of impacts for network congestion. One that may not be well understood is how it limits scale. So everyone should be familiar with Amdahl's law and the ability to shorten the completion time for a workload by adding more parallel processing to it. So in the original law, as we have increased scale, more processes running, the time to complete the parallel parts of the operation goes down, which means your workload will complete faster. But when we take into account the impact of network congestion, and here I'm showing it as latency as an additional time here, what we see is as we increase the scale, although the parallel compute time goes down, because there's more communication going on as the scale of the workload increases, the impact of latency gets larger. And so you can actually have more processes running on a workload and actually see no benefit in terms of overall workload completion time. And of course, there's more impacts than just workload scale. First is that if you have congestion, you'll get high tail latency. High tail latency means you'll have extended and unpredictable workload completion times, which as a research scientist means you're waiting longer for your results. And of course, we talked about how it limits scale. We also have a reduction in workload capacity. If each of my workloads on my cluster is taking longer to complete, that means I'm running fewer clusters at the same time. And of course, that means job queues will get longer, and my scientists, my researchers are waiting longer to get their jobs started. And we talk about it from a business context and efficiency. While congestion is occurring, a lot of resources in the cluster will be idle, and those are expensive resources. And that means that the cost of workloads has gone up. It means less work can be done, and the return of investment on your cluster has gone down. So broad set of impacts simply due to network congestion. When we take a closer look at network congestion, it occurs on a couple of time scales. There's short time frame congestion and long time frame congestion. We'll start with short time frame. Here I'm showing multiple flows of packets arriving at the same switch, and forwarding rules of that switch show that those packets are all going to be going out the same egress port. Now, if all these packets are on the way, so there's nothing the switch can do as they arrive, except try to egress them out the port, but in this case, there are more packets arriving that can be sent. So the only thing the switch can do is hold on to those packets to buffer them. Of course, that leads to a spike in latency, gets high tail latency, and your workload completion times are extended. Now, if the contention for the switch resource lasts long enough, there are a couple of things that modern switches can do. The first is use flow control to slow down some of the flows. And the second is to use adaptive routing to steer traffic away from that switch. But the key thing to realize here is, regardless of what you do in long time frame, all congestion starts out in the short time frame. And your performance of your network is really only as good as how well it responds with short time frame congestion. Now let's talk a little bit about the Rockport architecture. So what Rockport has done is gotten rid of the centralized switches that are common in today's traditional network environments. And we've gone from a centralized model of switching to a distributed model of switching, where the switching function is actually included in each of the endpoints in the network. So here we're showing a diagram of multiple nodes within a network and are directly connected together. There are no intermediate switches. The switching itself is done by the nodes. You can see that there are multiple paths available through this mesh topology, which allows us to have very high path diversity. So it's a direct interconnect architecture. Rockport has decided on leveraging a standard Ethernet interface for broad application and library support. And we've distributed a lot of the common functions you see in the network to the endpoints themselves. We have distributed routing and distributed control planes. And because we've moved the switching function down to each node, we have a linear scaling capability. You don't have to worry about whether there's sufficient centralized switching available to add more nodes, because really the nodes are bringing along a switching function with them. So we have perfectly linear scaling capabilities. And we have a very rich roadmap of field upgraded firmware releases, and we are currently supported in the latest MVAPICH library. So the solution itself is composed of three major elements. The first is what we call a network card. We call it a network card instead of a network interface card because it provides both the host interface and the implementation of the network function itself. So the card goes into a server and provides 300 gigabits per second of bandwidth on a single passive cable that goes to another passive element we call a shuffle. And the shuffle is completely passive, no moving parts, no power, and it simply distributes the 12 links that compose as 300 gigabits to create very rich mesh topologies. We'll go into these components in more detail in a few slides. And then we have the autonomous network manager, which provides never before insight into what's going on in the network on a per job basis, allowing operators to truly understand what's happening in the network. And we record all the information from the network for a full 7 days, which allows very rich troubleshooting and views into the past to see what was happening when my workload is running. Now, our network is a distributed function network. The switching is distributed, the control plane is distributed. So the first thing that happens when a node enters the network is it says hello to its neighbors. In our solution, we have 12 direct neighbors, but that would be a very complicated diagram. So I'm going to be using a simple diagram here showing 4 direct neighbors instead of 12. So the first thing that happens is I say hello to my 12 neighbors. Those neighbors exchange information, and then they exchange topology information, so that each node in our network has a complete map of the entire network. But each of those nodes will then start pre-computing multiple source routes to each of the known destinations in a distributed fashion. Here I'm showing this source node calculating routes to this destination node. Again, this is a distributed function. There's no centralized authority determining these routes. So this source node will use one of its 12 ports, 4 of course only shown in the diagram, and try to find the shortest path through the mesh topology from this node to this node using the blue egress port. The next thing that happens is that source node will say, well, what is my shortest path using my next port, the yellow port here? There's a rule that says you can't reuse a link. So what is the shortest path without using any of the blue links? Then what will happen is it'll use its green port and say, what's the shortest path through the network, not using any blue or yellow links? And it goes through this process to calculate 12 physically independent routes from each source to each destination. We use those routes to distribute the load across the mesh topology live on a per packet or per flow basis. And the algorithm we've generated to create these routes creates deadlock-free routes with very rich path diversity on fully populated sparse topologies, whether or not there's any failures in the network. And then on a data plane point of view, we are Ethernet based. So again, broad coverage on the host interface side. But as soon as an Ethernet frame is generated, we have a segmentation and reassembly function. So the packet is segmented into small pieces, into small flits, and those are then forwarded through an embedded flit switch on each of our nodes. So you can see that there's a source node that's breaking a packet up into multiple flits. Those flits are forwarded by its local flit switch to an intermediate node that forwards it on to the destination node, whereby the reassembly function recreates the original packet. And what this allows us to do is have extremely good control over latency and performance at high scale with very heavy load. And we have zero congestive loss within our network as well. So one of the key aspects about our networking is that we have very high path diversity. That means we have a large number of routes pre-computed to get to every known destination. We use the 8 optimal of the 12 pre-computed source routes to distribute the load to avoid multiple congested paths using our adaptive routing algorithms, and immediately react in hardware in case of local or remote link issues. We react in microseconds whenever any issue is detected in the network from a distributed point of view. The advantage of breaking things into small pieces into these splits is that it allows us to maintain very good performance under very heavy load. Here we're comparing a traditional frame-based switch on the left with our flip switching on the right-hand side. Here in a traditional frame-based switch, we have 3 workloads forwarding traffic from the same egress port. The first 2 are sending large blocks of data in 4K frames. And then a latency-sensitive message is coming from a different workload, and sometimes it gets blocked by multiple 4K frames, which of course introduces a spike in latency, which extends your workload completion time. In our flip switching mechanism, because everything is even broken up into small pieces, latency-sensitive traffic can cut in line on the buffers and be serviced very, very quickly. In fact, the average blocking time for latency-sensitive packets within a Rockport environment is only 25 nanoseconds with a ceiling of 50 nanoseconds. So almost no perceivable difference in performance between unloaded and loaded switching times. Our initial target topologies are 6-dimensional toruses. I think most of you will be familiar with the torus topology, but we have modified the behavior of a traditional torus. The first says we do support sparse, unbalanced topologies. You can easily scale in and scale out. We have our distributed deadlock-free routing, which provides very high path diversity, even with node or link failures. We have a very simple modular wiring approach, as you'll see in a few slides. And we have all the major operations in the network distributed to the nodes to allow excellent scaling characteristics. It's self-discovering, it's self-configuring, and it's a self-healing network. Let's go through the components in a little more detail. So this is the network card. It's a half-height, half-length PCI Express card that goes into a server or storage enclosure. And we do have in-box drivers available already for multiple Linux distributions, VMware, Windows. And it appears to the operating system to be an industry standard Ethernet NIC, which gives us very broad coverage for application and software stacks, both sockets, verbs, interfaces. We have 300 gigabits per second of network bandwidth out of this single connector here, running across a single fiber optic cable. But 100 gigabits per second of host bandwidth available to the applications running on the server. And all of the Rockport network functions, the data plane, the control plane, are performed by the embedded hardware. So there's zero load on the server to run a Rockport network. Now, to deploy a Rockport network, we've made it a very simple process. The first thing that happens is you plug in a network card into a server or a storage enclosure. It's recognized, of course, as a standard Ethernet NIC. We then plug in a passive fiber optic cable from the network card to the shuffle, and that's it. There is no step free. There's no configuration. There's no centralized authority required. The cards discover themselves. They discover the topology. They share topology information. They create a rich set of source routes, and they start passing traffic. It's a very simple to deploy network. You get access to very powerful supercomputer topologies like the torus without having to know really what you're doing. The network knows what to do. Plug in the card, plug in a cable, and you're up and running. Now, the shuffle itself is a pretty interesting device. Again, completely passive. Here we've taken the cover off to show you how it works. What we have are 24 green ports in this model. The nodes are for node cables to plug into, so from a card to one of these green ports. And what you'll see inside this box is a bunch of fiber optic cabling. Again, no moving parts, no power, completely passive. And if in my topology, I have a direct connection between 2 nodes, say node 1 and node 5, you could trace the blue cables here carrying the fiber optic strands into this metal box, where each pair of fibers is routed to create the topology required. So in my example of node 1 and node 5 being directly connected, you will have a fiber pair going from the node 1 cable to the node 5 cable. So without knowing what you're doing, by plugging in a single cable, you're using the pre-wired supercomputer topology within a shuffle to get access to all the rich capabilities of those topologies. The shuffle itself has two sets of ports. We've talked about the green node ports and how it distributes the physical links to other ports. We also have trunk ports. Trunk ports are used to get scaling beyond a single shuffle. This is a modular system, allows us to create networks of varying scales. As a simple example, we can talk about a 96 node deployment. So here, what I'm showing are 24 nodes in each rack directly connected to a shuffle. And what we have are 3 trunk ports connected to an upper level shuffle from each of those lower shuffles. These are MTP32 trunk cables, each containing 16 physical links. And what the upper level shuffle does is it creates optical connections between all those lower shuffles. It's another completely passive device. What we're showing here is a way of extending passive physical connectivity to create very powerful topologies. So as an example, what we see here is node 1 in this shuffle is connected through these cables to create a direct connection between the racks. A pair of fibers of a link goes from this node through the shuffle, follows these cables, goes back down, and ends up on the node 1 here. So what we're creating is a direct connection between nodes in different racks. Those connections are created to form a ring, extending dimensionality of the torus itself. And one of the interesting aspects is because we're creating direct connections between racks, we're removing the requirement to place workloads within the same rack. There's no locality requirement. So as you have a multi-workload environment and you get partition, I can't remember as your workload consumes resources unequally across the network, if you want to create a larger scale workload, it's unlikely you'll all fit within the same rack due to limited resources available. Performance within a Rockport network, that doesn't matter. We have direct connections between racks, so locality is no longer related to physical location. So from a management point of view, again, Rockport is all about creating powerful networking at scale in a simplified way. This is a key aspect of our technology. What it does is allow end users to very easily configure, manage, and troubleshoot our switchless networks. It presents in a very unique way these very rich topologies to allow end users to understand exactly what's going on with the network from performance and a diagnostic point of view. We have rich northbound APIs to allow third-party applications or scripts to retrieve very detailed reports and monitoring and management data. And as I said before, we store all the data that we collect from all of our endpoints for a full 7 days. So you can see in the GUI, there's a slider at the bottom that allows operators to move forwards and backwards in time. So if there was a workload that ran in the previous 24 hours, as an example, that had some challenges, you can scroll back to see exactly what was going on in the network on a per job basis to truly understand the network load at the time and how the network was moving that traffic across from point to point. We do have SNMP track capability to alert a centralized management station if one exists, and it is a very scalable architecture with a secure design. So next, I'm going to start talking about benchmarking. Well, it's nice to talk about congestion and the issues, and we do have a very unique switchless architecture. But what does it really mean to workloads? So the first thing that we want to make sure is clear is that typically you run a network benchmark on an unloaded network. So the only thing running on that network is the benchmark itself. And that provides a good baseline, best case view into the network, but not many networks are unloaded when you're running production workloads, especially in a multi-workload environment. So what we like to do is actually have loaded networks as a key performance aspect to predict how well workloads will run in a production environment. What we do, along with our partners and our customers, is apply load to a network at the same time as running the benchmark. We use standard tools like IV send bandwidth and iPerf to generate that traffic in order to have a controlled, repeatable environment. So first, what we're going to do is compare the performance of a traditional Ethernet network with a Rockport network. So the test setup is quite simple. What we have is an 8-node network, and each of these hosts is actually dual connected to both a traditional Ethernet network as well as to the Rockport network. And we have 2 nodes on each side of the network, which are running the OSU latency benchmark. We run that latency benchmark in an unloaded way just to get a baseline performance. And then we add congestive traffic from the left-hand side to the right-hand side in both environments to see how well the network now performs when there's additional load. You can think of this congestive traffic as other workloads doing large messages or accessing storage. It's heavy workloads that can interfere with latency sensitive traffic. We run it with two different configurations on the Ethernet side. One with no oversubscription, where there is 400 gigabits of capability on the bottom of the switch and 400 at the top, and with a 2-to-1 oversubscription, where we have only 2 uplinks or 200 gigabits per second going between the switches. So on the left-hand side, what we're showing is the no oversubscription design of a network for the Ethernet side. And you can see that the unloaded performance of Rockport compared to the loaded performance is pretty much equivalent. There's very little impact to the Rockport network for adding the additional load. Whereas in a traditional Ethernet environment, there's a significant increase in latency. And a significant increase in latency, of course, will drive an extended workload completion time. When we look at the oversubscription case, of course, the Rockport data is unmodified. You can see now that the impact to the OSU latency benchmark is pretty significant. We're adding about 100 microseconds of latency, which would be very significant to workload completion time. So Rockport delivers low latency under load with predictable performance. Now, one of the aspects of a Rockport network, of course, is that we have excellent path diversity. So what we wanted to do is test the network with in a very constrained environment. So what we've done now to the exact same setup is restricted both sides to a single link. So on the Ethernet side, we have single uplinks going from each leaf switch to the spine. And in the Rockport environment, we've disabled a lot of the links in a network to ensure that the traffic is flowing over a single link. So in both cases, we're congesting a single port within the network, either the external centralized switch for the Ethernet side or the embedded flip switch in the Rockport side. And we run it with 3 sets of network conditions. The first is in an unloaded manner. So from this node, running an OSU latency benchmark on both sides, and then running with IV send bandwidth as a congester between 1 pair of nodes, and then we run it with all 3 pairs of nodes. You can treat that as light congestion and heavy congestion within the network. And you can see when we restrict the bandwidth available, we constrain it to a single path. Rockport again has excellent performance under light load. What we have here for Ethernet is an increase of about 10 microseconds of latency. And when we go into the heavy load on the network, Rockport again has very consistent performance, and Ethernet has gone up about 50 or 55 microseconds of latency. So pretty significant impact on performance. You can see that Rockport provides low latency under load, even in a constrained path environment. Now we'll do some comparisons versus InfiniBand. Here we have a slightly larger system, 12-node system, and we have a 200 gigabit HDR IV switch network, 2 layers of switching. And again, we'll be running the OSU latency benchmark from one side to the other, and then adding congestive traffic. And I'll note this has no oversubscription. These are 100 gigabit hosts connected to 3 200 gigabit uplinks. So 600 gigabits on the bottom and 600 gigabits on the top. And similar setup on the Rockport environment. Again, the same hosts, dual connected to both the InfiniBand side and the Rockport side. Here, what we're showing on the left-hand side is the unloaded latency results. You can see that InfiniBand currently has an unloaded latency advantage. Rockport here, we're showing the multiple paths being utilized as we move traffic across the network. Here, we're showing 20 different runs of the benchmark overlaid on top of each other. But when we load the network, when it becomes a more production-like environment, when there's other traffic on the network, you can see how the Rockport performance is very, very consistent as it was before. On the InfiniBand side, there's a lot of variation now, as those the buffers within the switches are getting filled with the competing traffic. So you can see it's high variability and higher latency than it was before. There's about a 3x advantage for Rockport in this environment. But again, we wanted to say, well, let's restrict the testing to a single path. Let's see how these networks perform when you can't use any adaptive routing capabilities, when all you're doing is seeing what is the performance of the switch under load. So same setup, very similar setup to before. Here I have my 8 nodes in my InfiniBand environment and 8 nodes in the Rockport environment, the same nodes. And we've restricted the uplinks to a single port, so we know where the traffic is going to be going. And on the Rockport side, we've disabled a lot of links within the network, so we know where the traffic is going. All the traffic from the left to right on a single link, same on the InfiniBand side. So again, we run the OSU latency test with no additional traffic. Then we run it again with one pair of nodes generating congestion, another time with 3 pairs of nodes. Oh, sorry, I'll correct that. In both cases in the results I'm going to be showing, it's 3 pairs of nodes congesting on both sides. In one case, we have 100 gigabit hosts, and another one we have 200 gigabit hosts. So a slight difference in the test setup and the Ethernet side. And what we see is, again, the Rockport environment has consistent low latency under load, very little difference in performance. On the InfiniBand side, depending on if you have 100 or 200 gigabit hosts, you're approaching 10 microseconds on the OSU latency benchmark. So in Rockport showing low latency under load with predictable performance. So there is another benchmark I'd like to share with you. This is called the GPC Net benchmark. Some of you may be familiar with it. It's based on the 2019 paper from Argonne, Lawrence Berkeley, and Cray. And the idea is very similar to the congestive tests I've been showing you. So it's running a latency and a bandwidth test over an unloaded network, then rerunning it on a loaded network, in this case with 4 different congestion patterns. And the main metric reported by GPC Net is called the congestion impact. And it's what is a ratio of performance under load over the unloaded performance. So in other words, how much worse did the network get under load compared to when it was an unloaded network. So in the Rockport results, what we're using is a 48 server cluster. You can see the details here, 1,536 total cores. And the topology we created to create this network is based on a 4x3 by 2x2 torus. And the Rockport results, I think it shows a very strong demonstration of a latency consistency under load. The results of our GPC Net run are 1.0. And of course, 1.0 means the performance of our solution under load is the same as our performance unloaded. In the 99th percentile, 1.3 is the worst ratio that we report. But it compares very favorably to other networking technologies, like the previous Aries generation, EDR InfiniBand, and also very well compared to Slingshot as well. So the key takeaways here is that the real cost of congestion is being exposed. It's not just about network performance, it's about workload completion time, it's about predictability of performance, it's about workload queues, it's being about cluster efficiency and return on investment. Rockport has a new switchless direct interconnect that's very good at providing consistently low performance, consistently excellent performance, low latency under load. And we are talking to our partners and customers, and they're very interested in using these loaded measures to gauge the performance of a network, as the unloaded benchmarks, again, only provide a baseline best case performance metric, and not very good for predicting performance under load in production. All right, so there is an additional Rockport session tomorrow at 2 p.m. Going over the upcoming MVAPICH 2 design enhancements for Rockport switchless network. Don't miss that. And so thank you. Thank you for the time, and any questions?
Yeah, Matt, there are a lot of questions on the Q&A boxes.
Okay.
Can you take a look, or I can read it out for you?
Oh, I can take a look. Hold on.
Yes.
All right, so first one is from Paul Kenyon, I believe.
Yes.
How is congestion to a host handled? If a host interface is only 100 gig, if 200 gig of inbound traffic destined to the host is inbound on a physical interface. So yeah, we have very powerful congestion management features, including ECN and internal congestion management controls that allow us to very quickly push back on source hosts if the incast of a traffic exceeds what the host can take. So we can't go through in much detail here, but happy to follow up in another technical discussion one-on-one to talk about how exactly that works. Next question is from Craig Dunwoody. Is a passively cooled host card on the roadmap? And yes, the existing card today has an active fan. There is a passively cooled host card available in the first quarter of next year. Okay, next one, also from Craig. Lots of questions from Craig. Any expectation when more tech details were available on our website? Yeah, we continue to add more and more technical details. We were in stealth mode early in the year. We've come out of stealth, and we will be adding more and more details and talking more and more about the technology in events like this MUG conference. So it'll be over the next few months, you'll see more and more details. And if you're looking for information now, obviously reach out and happy to go through it one-on-one. All right, next one from Craig. What is the largest Rockport fabric tested to date? We've tested about a 400 node network and excellent performance. We also use modeling and simulation to go to tens of thousands of nodes. So in terms of physical deployments, it's in the hundreds. And like I said, modeling and simulation will go much larger. Does the roadmap include Gen 5, Gen 6 host guard? Absolutely does. Did not share the roadmap information now. And again, happy to go through it one-on-one, but absolutely. We have a rich set of not only firmware features for the existing platform, but additional hardware form factors for hosts at higher PCI bus speeds, as well as for other embedded solutions. And does the roadmap include 56 and 112 gig signaling per link? Absolutely. Yes, one of the key aspects of forming these large mesh topologies is to have a balance between the host and network bandwidth. There are lots of ways of accomplishing that task. You can either have more connectivity. We have 12 links today. We can, of course, increase that, as well as increasing the capacity per link. There are upsides and downsides to each approach. As you go to the higher link signaling, of course, PAM4, you get requirement for FEC, which can add a lot of additional latency to the link. So we have flexibility in that architecture to solve those challenges lots of different ways, and you'll get more insights into that over the coming months. And Craig, if you'd like to reach out, feel free.
Okay, so Matt, thanks a lot. Are there any other questions? We have enough time. We can have more discussions. Please post the questions under Q&A, or we have the Slack channel open also. Or if you just raise your hand, we can unmute you.
It's funny, when I timed this, it was almost an hour, so sorry I ended early.
No problem.
Not a problem.
Yeah, so I have a question. So is shuffle analogous to a passive or a dump switch? Like you have already pre-wired the connections and decided the connections in the switch, something like that.
Yeah, so the switching itself takes place within the active network card. So there is no switching going on within a shuffle. This is simply taking the 12 physical links within each of the cables on the node. If you can see sorry. There we go. My QA thing was covering it. So what happens is we have those 12 physical links for 300 gigabits of aggregate bandwidth coming from each card. Those are routed and by the shuffle to simply distribute those links to where they need to go. Some of them are connected locally within the same rack, as you can think of it, and some are used to create direct connections between racks. So the shuffle isn't a switch. It's simply, you can think of it as a very intelligently wired patch panel, completely passive. The idea is that it allows end user operators to create torus topologies and other advanced supercomputer topologies very easily, simply by plugging in the single cable. There's no manually wiring. You're not connecting 12 different cables or more, create whatever topology you're targeting. You simply use one of our modular shuffles, and with that single cable connection, you created that supercomputer topology. So the idea is to allow advanced HPC users, large enterprises to get access to these very, very powerful topologies in a very, very simple way. Plug in the cable, and I have access to very, very powerful topologies with a distributed control plane. That means that you're going to get very high resiliency. It turns out a much lower power consumption as well.
So Matt, I have a related question. It's a hypothetical question. I know you have a flexible topology. Let's say somebody is deploying. They may select one topology. Do you advise, if they have some critical applications, they can also, might be for 5 days, they use one topology. Next 5 days, they change another topology. Do you recommend those or no?
We haven't so far. I mean, the idea is that the topologies we're deploying are very flexible and are designed for the performance characteristics of the different workloads required. The diameter of our networks are very small compared to traditional torus networks, as an example. We have other topologies being planned. We do expose topology information. We're working to integrate that capability within Slurm to allow easy deployment of applications on the Rockport network. The idea is that the advanced distributed control plane the very fast hardware reaction time to any issues or changes in topology means it's actually very, very flexible, can support multiple workloads. As you can see, if you have some heavy bandwidth workloads in the same fabric as latency sensitive traffic, there's no impact of the latency sensitive traffic. So you don't need to partition networks. You don't need to have dedicated networks for storage. The same fabric can support all those different use cases simultaneously while guaranteeing very good performance for those critical latency sensitive messages, as well as providing access to up to 300 gigabits per second of aggregate bandwidth for bandwidth sensitive applications.
Okay, thank you. So how do you see like the, I mean, you showed some of the like the latency sensitive things and all. If you take a look at like a very diverse workload like HPC, emerging ML, DL, how do you think your customers will try to deploy this?
Well, our fabric, I think it's pretty unique as being able to deliver excellent latency performance as well as very good bandwidth performance simultaneously. So really, we see a broad set of applications running on a network. Our customers have been running multiple types of workloads for over a year now through our beta process and our early trials. So we're seeing very good performance across a broad set of applications. The key is that there's no tuning required. There's no per workload settings you have to make. You don't need to figure out, well, how do I optimize my network for one workload, knowing that it'll potentially degrade another workload? Everything is done intelligently by the nodes themselves. They, at hardware speeds, have access to what's going on in the network and react accordingly. Wherever it's congestion or topology changes or failures or heavy workload, the design of a network was made with a goal of consistent performance under load at scale in a way that people can use it. You know, it's okay to say that under certain conditions with certain configuration parameters, you get certain performance. But most multiple workload environments, you know, they're pretty chaotic. It's very hard to make a design that's very good for everything. Designing for one workload versus another can be, you know, a compromise in those settings. So again, our network is designed to concurrently support these different types of workloads, provide excellent performance in a way that it can be deployed and understood by everybody. At the same time, we provide very rich, detailed information about what's actually going on in the network. You know, we're not a black box. We expose everything that's going on in the network, and we do it on a per job basis. So if I'm looking to see how I can optimize a job, is it about, do I rewrite the job? Do I place it differently if required? And what's going on? How is it? What kind of network load is it placing? You know, how can I squeeze more performance out of my workload? We provide all those capabilities. You know, distribution of packet sizes, wherever packets are going, and with top 100 neighbors, there's a lot of rich information provided by that network manager. As I said before, it can be done on a temporal basis, going back in time up to 7 days. So, you know, I run a workload next day, I see it performed at a certain level, I can go back and say, okay, is there additional load I can put in the network? Is it a network issue? Is it an application issue? How can I tune that workload? You have all the information you would need in order to make that determination. So it's a very powerful tool. And of course, that northbound API allows integration into any tool or data gathering system that may exist already.
Thank you. How about partitioning capability? Let's say somebody has deployed a cluster and they want like two different jobs with different communication characteristics to run. Can we do something so that this traffic don't interfere?
Well, it's funny. The native switching design means they won't interfere anyway.
Okay.
But in terms of partitioning, we do have that capability. It's on the roadmap. You know, we are FPGA based today within our network card, which provides for a very rich set of features and capabilities and performance improvements to be field upgradable by our end users. So customers have already upgraded in place our technology from one release to the other. So in terms of a single tenant environment, there's no need to do any kind of partitioning from a performance point of view. From a multi-tenant sort of cloud environment, where those features are coming.
Okay. Excuse me. How about interfacing with some parallel file system like Lustre, GPFS, those kind of things? Do you envision a little bit of different kinds of connectivity, or the same network should be able to handle both the compute nodes as well as the storage nodes?
Well, we've been tested by a couple of the large labs, you know, very large scale parallel file systems, and you have Lustre concurrently with sort of the MPI communication on the same fabric, because we're very, very good at maintaining latency performance, even under really maximum load, you can have those on the same network. We have that ability to ensure that regardless of these large transfers going on, whether it's like I said, access to storage, whether it's writing data, reading data, whether it's doing a dump of all the data so you can restore later, it doesn't matter to us. We see that traffic as small pieces, small flits. In a traditional environment, you'll see jumbo frames, you'll see very small messages interfere with each other. Our design simply precludes that from happening. Excellent latency performance under load. And I'll share on Tuesday a preview of what's coming up, jointly with MVAPICH and Rockport, showing what that exactly means quantitatively. I think everyone will be pretty impressed with what Rockport can do.
Okay. And so I'm assuming then you have done some kind of a congestion analysis, quality of service analysis in this kind of mixed workload.
Absolutely. So yeah, we'll be presenting some very detailed data on a preview of the enhancements that your team has put in MVAPICH, as well as within Rockport, to take advantage of what we've done. And I think you'll, like I said, be very impressed by how well latency is controlled even under extreme load in our environment. Again, it's the philosophy of the design, ensuring that regardless of what's going on in the network, the things I care most about, those small messages, always arrive on time. It's predictable performance. Workloads complete on time. I can plan my workload scheduling, on a sort of a larger scale basis and research scientists will know when a job will start. They don't get delayed by other workloads taking longer than expected because the network wasn't as good as handling heavy load.
Okay. So I've been asking a lot of questions. How about others? Are there any additional questions from people? Please post those on the Q&A button or the Slack.
I have a couple of questions.
Please,
so,
Bharat, please.
Yeah, so along the lines of routing, right? So you talked about torus topologies. So have you guys run experiments with any other popular topologies out there? Or
Yeah, and I will say one thing sort of very clearly. Our topologies are based on popular topologies. So, traditionally, specific topologies have very strict rules you should follow in order to get good performance. The torus one, a classic one, is you really want to balance torus. You don't want any failures, or some of the approaches that deadlock free routing will fail, and you get very poor path diversity. So we're focused on basing topologies on what's well known, changing a lot of their characteristics to get better performance. And yet we've done experiments on multiple topologies. The one we're currently designing for is a Dragonfly topology.
Okay. Okay, so so you try to design like routing algorithms which are optimal for a certain configuration, right? So do the nodes detect that like automatically? So let's say we set up a cluster with some irregular topology, right? So then what does it do? So do you have like something to detect whether it's a common topology and apply optimizations, or is it not like that?
The current approach we have, a deadlock-free routing algorithm, is actually designed for generic topologies. There's nothing in that algorithm that says do certain things on certain topologies today. It just, because most of the topologies we will see in the real world aren't balanced toruses. A certain number of servers will be in each rack. The configuration matches how the customer wants to deploy the equipment. So we're designed to be generic. You can have any generic topology, and we'll create a large set of source destination route pairs in the entire topology in a distributed fashion. This is a patent pending algorithm we've created that allows huge flexibility in topology design and deployment in production. Now, as we get into much larger scale, of course, optimizations are possible and likely to be made. But today, it's a very general approach because we know customers deploy the scale they want across a physical layout in the data center that makes sense for them, and trying to constrain what the customer does to specific topology rules just doesn't make sense.
Okay, so just along these lines, do you plan to expose any APIs or something so that users can decide how to route, or do you think that will be like a dangerous thing to do?
Well, the challenge with allowing customers to try to route is that means that they believe there's an algorithm better than ours. And I don't want to be too braggish here, but the algorithm we've created to create deadlock-free routes across generic topologies, fully populated or sparse with failures, it's not something many people can do. I mean, it doesn't exist, to be honest. So our capabilities, the distributed routing function we have, provides excellent latency characteristics and excellent bandwidth characteristics, regardless of topology. I think you've seen that with the constrained path testing I showed you. It's not a torus, it was a dumbbell design, and we still showed excellent latency performance and excellent bandwidth performance under heavy load. So it's a very good approach. It's a very generic approach that allows any topology to be supported and deliver excellent workload completion times, especially in a multi-workload environment.
Okay.
Now, just to add to that, it doesn't mean customers can't get access to the routes we are pre-calculated. So one of the things we can do, of course, is look at, well, if this is the current set of routes in the network, maybe there's an enhancement to workload placement that can be made. So that information is available, it's just not programmable. It's a read-only aspect of that system.
Okay, so that would help like tools or something to understand or visualize stuff or things like that, right?
Exactly, and our network manager, of course, provides a lot of very rich visualization tools, so people have insights into what's happening on the network. So it's not just an API, it's very easy to use visualizations we provide.
Okay, thanks.
Well, thanks, Bharat. And then some little bit futuristic questions, Matt. I mean, do you think your network will need any changes like for next generation GPUs or DPUs, those kind of adapters to be added to the system?
Well, the approach we've taken in terms of the design of our part of the solution, I'll quickly flip to a slide here.
Sure.
Right, there's really two halves to our card. There's the embedded split switching capability, really the implementation of the network half of the card, and then there's the host interface. So we've designed ourselves to be very flexible in terms of how that host interface is implemented. And we already provide strong support for future the advanced approaches like DPUs and GPUs. We also do have an FPGA on board. And of course, there are potential for enhancements to be added in the future to perform new functions, let's put it that way.
Okay. So I think that's all the questions I had. Anybody else, any other questions people have? So if not, we have a lunch break coming up.